So paper C3 of the June 2018 series. Oh, wasn't too bad at all. Now, I just want to say a few things. Overall, this paper was okay. I mean, some of the questions were quite difficultly asked, but otherwise, some of them were not too possibly difficult. Okay, I've already solved the whole paper, and these are just my solutions. Yeah, I've referenced student forum. I've double checked, various websites just to be as 100% accurate as possible. Yeah. I mean, if you guys spot any single inaccuracies in any single part, please let me know. But otherwise, without further ado, let's jump straight in. So here we go. Yep. Okay, number one. Here we go. So given that we got a typical equation, find dy over dx, giving your answer as a single fully factorized expression. Okay, now before you look at the solutions, when you differentiate this one, how do we know what to use? How do we differentiate this? Well, look at this, we can see that we got two functions. We have 2x and we have another one, 3x minus 1 to the power 5. Because we got two multiplied together, we use the product rule, okay? If it was 2x over this term, it would be the quotient rule. Okay, so that's two ways to differentiate. Now, when it says single fully factorized expression, this means that when you differentiate this one, not only do you use the product rule and sort it out, you would also have to tidy up completely, okay? Now, let's have a go. So typically, to use a product rule, you pick one variable as u and the other one as v. So my u is 2x and my v is 3x minus 1 to the power 5. And then you differentiate both. So I just wrote u prime. This means the du over dx and dv over dx when you differentiate. So differentiating 2x gives you 2. Now differentiating this one over here, 3x minus 1 to the power 5. All you want to do is firstly drop the 5 down, so you got 5 in front. And then differentiate the inside of the bracket. So differentiating 3x minus 1, you get 3. So then you should have 3. Then using that 3, multiply to 5 to get 15. And that's it. And then you copy the expression. And then dropping the power down by 1, as always. Okay, and that's it. That's literally done. This is essentially called the chain rule, by the way, yeah? So this also has a name. Chain rule. Okay. Now, dy dx, to use the product rule, is just literally like this. You do the v term times u prime plus u times v prime. So just like that, or other way around. So you can just say 2 times 3x minus 1 power 5. So just glue them together. Plus, and then u times v prime. So 2x times 15 will give us a 30x. Copy the rest. And now you just want to factorize, collecting like terms. This is the final answer, but to get to this one, all we have to do here is basically look at the expression and realize that they both have 3x minus 1, at least 4 powers of it, whilst this one has an extra power. So if you factorize 3x minus 1 to the power 4, and of course 2 outside because 2 goes into 30 as well, so having something like this, 3x minus 1 to the power 4, you'll realize now that on the left side, you still have an extra 3x minus 1 to account for it. Plus on the right side, to get 30x from 2, you got 15x remaining. And of course, you've used up all the 3x minus 1 to the power 4s. And then you just expand this, tidy up. So 3x minus 1 plus 15x will give us 18x minus 1. And that's it, fully factorized. Okay? So let me know if you guys understood this fully. Give me a like and so on. Otherwise, let's look at B. So hence, find the set of values of x for which the derivative is less than or equal 0. In other words, when this solution here that we just obtained is negative or 0. So we're going to find what x values make it negative or 0. So opening statement, dy dx less than 0. Copy this down exactly, and then you realize you can just cancel out the 2 because dividing by 2, you still get the same expression. Okay, now, what do we do here? So this one I use a true and false technique. So first things first, find your critical point. So what this means is that see when this one equals 0 and this equals 0. So you got 3x minus 1 equals 0. So x must be a third if you solve it. 18x minus 1, if that equals 0, solving it, x equals 1/18. Now, what I do here, and this means firstly that these are valid solutions, by the way. These are two of the solutions that will make dy dx less than 0 or 0. Okay. Now, putting this in ascending order, I put 1/18 here and 1/3 there. All you want to do now is put random x values that are less than 1/18, between 1/18 and 1/3, and greater than 1/3, to see if the answer is less than or equal 0, if it's true or false. It's true if it's less than or equal 0, false if it isn't. So for example, I'm going to pick an easy value for values less than 1 over 18. I'm just going to pick when x equals, say, 0. Okay? When you plug in 0 to this equation at the top here, you get 0 minus 1 to the power 4 and 0 minus 1. Solving this, you get negative 1. So you get a value less than 0, which is true. So the answer is true. So this means that for values less than or equal 1 over 18, it's true. So that's one solution. So we can say x is definitely less than or equal 1 over 18, because that seems to be true. And remember, this is if it's true for one value less than 1 over 18, it's true for all values, because 1 over 18 is the critical value. It's literally the turning point here. Now next one, between 1 over 18 and 1/3. To make this easy, just pick values between 3 and 18. So I'm going to say, I don't know, 1/5, yeah? Now if you plug in 1/5 here to replace x with 1/5, I end up getting a positive value, a value way bigger than 0. So of course this is going to be false. So this means there is no x values valid between this range. So this is false. Now picking a value bigger than 1/3, I'm just going to say 1, because it's easy. Plug in 1 over here, and you'll realize again you're going to get a value, because you're going to get what, 3 take away 1, which is 2 to the power 4 is positive, and then 18 take away 1 is 17. So you can get two positive numbers multiplied. Of course you can get a positive answer. So it's going to be false. So again, this is false. So that means there is no x values valid that's bigger than 1/3 that will give you a solution less than or equal 0. So that means the only possible solutions would be when x is less than or equal 18, or when x is exactly equal to 1/3. Because remember, these are valid solutions too. So we say that these are the valid pairs. So x is less than or equal 18, or exactly 1/3. So the function f is defined by the following. Okay? Show that this function can be written as a linear one, as in a over bx plus c, where each of these terms are constants. Okay, now if you guys haven't already spotted this, I want you guys to have a look at the last term, the 4x squared minus 25. This thing you have to immediately spot and realize that this can be factorized using difference of two squares. So I call it dots here. And in fact, 4 squared minus 25, if you use the difference of two squares, i.e. the double bracket method, the way it works is that you square root 4x squared, and which will give you 2x on both, and square root 25 will give you 5 on both, with a plus minus sign attached. This is literally the difference of two square numbers, with 4x squared being one square number and 25 being another. So this is something we have to literally spot from the get-go. Otherwise you could make a really big mistake. Now that's alright. So when you do that, you'll realize that in fact this lower bracket here is actually made up of 2x plus 5 and 2x minus 5. So essentially, when you combine this to a single fraction, you need to make sure that every single denominator has the same terms. So for example, the first fraction is missing 2x minus 5. So this implies that you're going to times up and down by 2x minus 5, whereas the second fraction is missing 2x plus 5. So times that by 2x plus 5 up and down. Okay. So when you do that, you can actually combine this to a single fraction. So it looks like this. So timesing 6 by 2x minus 5, timesing 2 by 2x plus 5, and then adding all these together, all over the common denominator, you can then simplify it. So now all you have to do is just literally tidy up. So what I just worked to the top half of the fraction just to save time. And this is what I recommend in exam. Don't waste time repeating the fraction over and over. Just write a little note, okay, I'm working with the top half only, and just expand and simplify. And then when you get to this stage, factorize as much as you can. In this case, you can only factorize 8, and voila, you got 2x plus 5 on the top half. So essentially the function becomes something simple. And then you can just cancel out, and you're left with 8 over 2x minus 5. And that perfectly fits the a over bx plus c. That's it. All done. And if you want to finish this off, this means that where a is 8, b is 2, and c is negative 5. Now, yeah, really easy actually. Now, let's look at part b, yeah? So find the inverse function and state its domain. Now, quick tip here. The domain and range of an inverse function is actually the opposite of the regular function. For example, here we see that the domain of the regular f is 4, is x greater than 4. This implies that the range of the inverse function is also bigger than 4. So domain of function equals range of inverse function. So I made a note here somewhere. So this is something useful. So the range of fx equals the domain of the inverse of fx, whereas the domain of fx equals the range of the inverse. So a very useful tip. Now let's go ahead and crack this down. Yeah, so to find the inverse, always start down with this step here. So I always say let x equal the function of y. In other words, this is a function x from part A, and then therefore just copy it down. So this means x equals function of y. So replace this function here with y. So you got 8 over 2y minus 5, and then we have therefore x equals 8 over 2y minus 5. So you can kind of see we just literally flip the letters around. And to find the inverse, just make y the subject. So here we can multiply 2y minus 5 across to clear the fraction, expand the bracket on the left side to get 2xy minus 5x, and just rearrange to make y the subject. So what I did is I added 5x across and then divided 2x to get something like this. And then looking at this head on, we can see straight away the domain here, which is like what values x can take. When you have a fraction, and always remember this, is that you cannot divide by 0. So in other words, the bottom half cannot equal 0. That's why I wrote 2x doesn't equal 0. Therefore, x doesn't equal 0. So this is the domain. This means that we can say for certain that x cannot be 0. Now, there is more values, and that's something where it can actually slip you up. The only way to find more values is to go back to the original statement that said x is greater than 4 for the function and realize that's the range. Now what I would do here is let's just work with the regular function for now, and I'll show you what I did. And I advise you guys do this for all the questions. So I would make a table for the original function, yeah? Whatever you get for the range, that's going to equal the domain for the inverse function. So let's find the range of fx. This will pretty much give us the domain of the inverse. So what do we have? So let's start with, since x is bigger than 4, let's start with value 4. Because if you plug in x equals 4, you'll find out the value where it cannot equal. So when x equals 4, I got 8 over 3. And then I tried other values. So let's try increasing values. So plug in x equals 5, you get a slightly smaller value of 8 over 5. I tried 50, you got 8 over 95. So you can see so far it's getting smaller, right? Now this infinity sign, this is just literally me in the calculator smashing 99999. If you try it in the calculator, you're going to get an answer which is so close to 0. So basically what it means is that if you keep, putting more 9s, you're going to get an answer which isn't 0 but close to 0. So we can see that the value starts from 8 over 3 but not at it, but then quickly shrinks down to 0. So we can say that the range is clearly from 0 to 8 over 3. And if that's the range of fx, that means the domain of the inverse is just the same thing but with x. That's it. So remember, range is the y-axis, domain is x. So this is really a little quick tip. If you guys understood it, please let me know. If you want more clarification this one or more examples, again, let me know in the comments, and I'll try and hook you guys up with more practice. So it says that the value for car is modeled by the formula v equals 16,000 e to the negative kt plus some constant a, where v is the value of the car in pounds, t is the age of the car in years, where k and a are both positive constants. So every time something is a positive constant, and always remember this, is that the numbers here are fixed. So every time you get other related problems, don't forget that the k and a values are always going to be the same for each and every problem, yeah? Just a quick tip. Now, here we go. So given that the value of the car is 17,500 quid when new, okay, keyword new means when the time is 0, when it's fresh off the bat, and 13,500 pounds 2 years later. So again, when t is 2 at this valued price. Find the values of a, show that k is this, and of course we'll get to c in a bit. Now, I'm going to go ahead and show you how I did part A. So I just said, okay, so since the car is new, this implies t is 0. So that means the value of the car is 17,500 pounds. So all you want to do is use your original equation here, plug in the value for v at 17,500, plug in the value at t equals 0. So quick recap, e to the power 0, 0 times anything is 0, e to the power 0 is always 1, anything to the power 0 is 1. So you're just left with 16,000. Rearrange and make a the subject, and voila, 1,500 quid. And that's your constant for a. So that's it. So that's a done, 1 mark, so not too bad. Now show that k equals the natural log of 2 over root 3. Now you can get this one by using t equals 2, the second part, second information. So I said, okay, so the value of the car is what they told you when t is 2. Using the original formula again, plug in what you know. So we got the value at 13,500 here. We got the value of a being 1,500. And we know t is 2, so k times 2 is 2k. Got that there. And just rearrange to make the e value the subject. So I firstly subtracted 1,500 from here to get 12,000, then divided 16,000 and simplified this to get 3/4. So now we're at this stage. We've got e to the negative 2k equals 3/4. And now the rest of the steps are easy. To get rid of the e, remember you can use this opposite, which is the natural log, i.e. ln. And when you got ln times e, it cancels them out and you're left with minus 2k. Of course, you could do ln on both sides, so you have ln 3/4. And finally, just divide minus 2 across, so you get minus a half times ln 3/4. And be very careful here, because unfortunately your calculator will not give you this expression. You would have to find case step by step. So what I did, I used the log rules, and I realized that anything, a value in front of the log will become a power. So it will become 3 to the power negative half and 4 to the power negative half. So a bit like this. And working them independently, anything to the power half is square rooting. So this is square root 3. When you got a negative sign, it's the reciprocal, so it's 1 over root 3. Likewise here, this is 1 over square root 4, which is 2, so 1 over 2. And because they're both 1 overs, just flip them upside down to get 2 over root 3. This part you can put in a calculator and you should get that. So that was easy. As for the last bit, C. Find the age of the car in years. So in other words, for you mathematicians there, find the value t when the value of v is 6,000. Easy. So just substitute 6,000 for v here. Substitute, and then just find the value t. You got everything else now. You got k, you got a. Just find t when v is 6,000. So what I did here, I mean, I didn't put the value k now because this value is just going to kind of make your calculation more complicated. So just call it k for now. And just work your way through it. So replace v with 6,000, subtract 1,500 across to get 4,500, divide 16,000 and simplify this to get 9 over 32. Again, making the e value the subject, taking the ln on both sides, so e and ln cancel out, so you're left with minus kt equals ln 9 over 32. Divide minus k across, so you got the value. So you got the value t. Now you can put the value k back in, which was what, ln 2 over root 3. Smash this all in the calculator and you should get about 8.82 years. Okay, so it tells us that we have a figure 1 which shows a sketch of part of the curve C, which is this U-shaped quadratic one with the given equation. Okay, so here's the equation. Now just look at this head on. Okay, we can see that this curve cuts the line at 2 points A and B. We can also see that at point A, it seems to cross the y-axis. So we can guarantee that this point here has an x coordinate of 0. Because when something cuts the y-axis, the value of x is always 0 because it hasn't moved across. Now to find the y value, all you do is just plug in the value of 0 into either equation of the curve of the line. But because we have the curve equation, just replace x with 0 here. So you're going to essentially have, on this part here, e to the negative, in this case 0, so e to the 0, plus 0 minus 3. And e to the 0 is 1, so 1 minus 3 will give us negative 2. So that's the coordinate A, okay? And that's going to help us later. Now, carry on the reading. So the curve C crosses the y-axis at point A. The line L is the normal to C, keyword. Now, if this is the normal, this means that at some point there was a tangent, which was a straight line, and the normal will therefore make it perpendicular at this point A. So essentially, you can just find the gradient of this normal by firstly using dy of dx, differentiating this equation, and placing the value of x, which is 0, and then taking reciprocal to find the perpendicular gradient. So let's have a go. Let's find the equation of this line in this form, y equals mx plus c. Okay, so first things first, let's find the gradient, yeah? Now, I did it here already. So I said, okay, let's have a look. So using the equation here and trying to find the gradient m, just go ahead and differentiate this. So dropping the power minus 2, so differentiating exponential, we should get minus 2e to the negative 2x. And then for x squared, drop the power down, you get plus 2x. So nice and easy. And then to find the gradient, well, to find the value of dy dx first, we just do it at point A. And this has an x coordinate of 0. So plug in 0 for x for both of them. You should put this in your calculator and you should get about negative 2. So that's the value of dy dx. Now this would be the gradient if it was a line of a tangent. But because it's a normal, we just take the reciprocal. So it's going to be plus 1 over 2. And that's our gradient. Hence, for y equals mx plus e, so remember this is a line equation of a straight line, you just replace m with positive half. And so far, our equation looks like this. Okay. Now to find c, just plug in any point on that curve or that line, and we got 0 minus 2. So replace x with 0, y minus 2, you should get something like this. Minus 2 equals 0 plus c, and therefore c equals minus 2. And hence our final equation, replacing c with minus 2, we have half x minus 2. And that's it, guys. That's the equation of the tangent, of the normal. Now let's look at part B. So the line L meets C again at point B. Okay, so we're talking about this point here. So again, this is simultaneous equations if you guys haven't seen. Since we got the line, the new line, which is y equals half x minus 2, we're more or less going to solve this simultaneously now. Now, show that the x coordinate of B is the solution of this one. Now, all they're doing here really is just rearranging these two equations, but they're not technically solving for x because we have x in multiple places. Okay, so let's have a look and just solve this simultaneously. See if we can prove this result. Now, part B. So I've already started off like this, and this is the objective. Now, if you can see carefully, my tip is to work backwards, yeah? Notice how we got a square root. If we squared both sides, the square root will go, so it looks a bit like, let me just cross this out. So we have x squared equals this term. And looking at the equation, I would just go ahead and make x squared a subject for now. So we could plus 3 across and then minus the e term. We're going to have, therefore, x squared equals half x. Okay, so adding 3 across, minus 2 becomes plus 1. And subtracting the exponential, we're going to have a negative e to minus 2x. Okay, so at the moment it's the same thing. Now you just rearrange the position here and say, therefore, x equals the square root of 1 plus half x minus e to negative 2x. And that's it. That's part B done as well. Now for C, let's have a look. So using the iterative formula, so again, it's the same thing, replacing x with xn plus 1, whereas the x's inside become xn and xn. So using the initial value x1 equals 1, find the next two values. Okay, there's a nice trick here. And the trick for this kind of question is to use a calculator and using the answer button in the calculator. What I would do is firstly press 1 in your calculator, then press the equal sign. And when you do that, you're going to automatically save the value 1 in your calculator. So that's going to be your answer. Now what I would do, copy this formula down, but replace xn with your answer button. So yeah, so what happened here is that your answer value is currently at 1. And what it's going to do, every time you press equal with the button answers here, it's going to automatically find the next values up. So it looks a bit like this. This is what should be in your calculator. And when you do that, making sure the answer is initially 1, pressing equal the first time will give us the next value for the answer, which is 1.168 and so on, rounds to this value. And pressing equal again without touching nothing will give us the x3 value. And if you keep pressing equal, you're eventually going to get x4 and x5, so on. Eventually, I mean, you don't have to do this, but if you keep doing this after many times, the value will stabilize here. So this will be the true x value, but you don't need that. But yeah, guys, I hope this helps. And if you enjoyed this video, please give me a like, subscribe, share with your friends. Otherwise, I'll see you on question 5. Ciao. So figure 2 shows part of a graph of equation y equals fx. And if you see it, guys, we can see the fx is in terms of mods, okay? So before we finish the rest of this, how about we go ahead and label this graph and just see where it hits on the y-axis and what this point is here. Well, I can tell you straight away. If you look at this carefully, it says that the graph has shifted by plus 3. Now this means that it's gone up by 3. So this means that the lowest point here must be 3. Okay. Secondly, another way to find out what this sort of turning point is, a sharp turning point, is actually the solution of the mod. So you got to think of it as like one of those bracket problems. You got 5 minus x. In this case, x would have to be 5. Because you put 5 here, you're going to get 0. And 2 times 0 gives you 3, which is y. So x must be 5. Okay. Now secondly, another point to consider is the one over here from the downward slope. Now to work out this point, notice how it cuts the y-axis. So if something cuts the y-axis, this means that the y coordinate fx must be 0. And because this is going in a downward slope, we know that the gradient is negative. So in fact, minus x is the gradient. So in fact, this equation as it is cool. So we can say, okay, when y equals 0, we have 0 equals 2 times 5 minus x plus 3. And then expanding this and solving it carefully, you'll realize that you're going to get x equals 13. And that's exactly where it hits. So now that's done. And oh yeah, by the way, this side is obviously an upward slope. So yeah, since that's done, let's go ahead and look at part A. So it tells us to state the set of possible values of k, knowing that the function fx equals k. When it says fx equals k, it means literally a straight line cut in the y-axis. Okay, that's literally just a straight line cut in the y-axis. It could be anywhere. It could be, say, fx equals 2. It would be a straight line. Now, this one we know has exactly one root. So this means the only place where it could potentially hit a single place will be firstly at 3. Like if you do the straight line here, you could hit this exactly at 1 point. Or any point above 13. Because if you look carefully, you can hit here or here and so on. If you hit anywhere between 13 and 3, it's going to be 2 points. So you can say that the set of possible values of k could be at k equals 3, or when k is bigger than 13. That's it. Okay, not bad. Now, next one. Solve the equation fx when it's set to half x plus 10. Now, these kind of questions are very important to understand. You have two equations, yeah? One line going down and one line going up, described by this equation. What this means is that for the downward slope, we have a negative gradient. So we have 5 minus x. Remember, there has to be a minus sign in front of the x. And because this is an upward slope, this means that the gradient is positive. So we have to rewrite this as x minus 5. This would be for the positive equation. So essentially, you have these two equations equal to this equation, and it looks a bit like this. So the downward slope looks like that, equal to the fx function, which is from here. And upward slope, you just swap it around to make it x positive and just literally just rotate it, as you see, and equate it to the second function. And now all you have to do is literally expand, solve it, and then you get your two solutions. So let's do it step by step. So expanding this, we should get 10 minus 2x plus 3 equals half x plus 10. Collecting, putting all the x's on the left side and the numbers on the right. Actually, you can just cancel out 10 right now. You're going to have firstly minus half x, so you're going to get minus 2.5x equals minus 3. And then dividing these from each other, dividing minus 2.5 across, it should get x equals, on my calculator, 1.2. Okay, and just repeat the same for the second. Expand the bracket, you get 2x minus 10, guys. Add 3 equals half x plus 10. Okay, and then collecting, move all the x's to the left and the numbers to the right. So in other words, add 10 across a minus 3 and subtract half x. You should get 1.5x here. You should get add 10, which is 20, subtract 3, and you get 17. This means x equals, when you divide by 1.5, 17 divided by 1.5 gave me 34 over 3. And yeah, this is the same as 6 over 5. Okay, part C. So what do we have? So the graph of equation y equals fx is transformed onto the graph of equation y equals 4 times the function of x minus 1 aside. And the vertex in the graph of equation 4 in the same thing has coordinates p and q. This is talking about the vertex that's in here. So this is the vertex pq. But of course, we need to find it for the new graph. State the value of p and the value of q. Okay, this is just transformations. So quick thing to note, when you got a number timesing the function, this means that the y coordinates have been scaled by 4. So we've got times all these y coordinates by 4. So for example, 13 times 4 becomes 26, 52, and 3 times 4 becomes 12. Of course, x values don't change because this just doesn't change. And when you work inside the bracket, when it says x minus 1, think of it as a solution. When you solve it, you get x equals plus 1. So this means you shift the x values by plus 1. So this means this 5 becomes 6, so it moves to the right by 1. This means this coordinate here, which is like 0, 13, is now 1, 13, so it's moved to the right like here, 1. So literally everything just shifts here. And then you just draw the same shape back. And then upwards. So yeah, remember to use a ruler, guys, yeah? And that's it. Yeah, sorry, that's my clock. So yeah, that becomes 52 here. This coordinate here is 152. This one here is 12, and this one here is 6. And that's it. So this means this vertex here is going to be 6, 12. So the value of P is 6, and the value Q is 12. 6. So using the identity for tan A plus B, solve for the given range, the following equation. Okay. Now for this one, we have to quickly just recognize it straight off the bat that tan a plus b, if we expand it, we're going to get the same expression here. So actually, this is identical to tan 2x plus 32. So that's probably why they gave it up here. Just they want us to notice the fact that this, if in its original tan form, is like that. Okay. So from here, this means that the left-hand side equals 5. So we can say, therefore, tan 2x plus 32 must equal 5. Now, to solve this, just tan inverse. So therefore, 2x plus 32 equals the tan inverse of 5. So let's go ahead and tan inverse it. And oh yeah, keep your answers into degrees mode, yeah? So tan inverse 5. And you should get, let's see, 2 decimal places. So 78.69 degrees. Okay. Now, this one's going to be quite straightforward. All you need to do is firstly realize that because you're working with tan, we're going to use a cast diagram, C-A-S-T, and just highlight T and A, because A means for all positive results, and T is tan because tan is positive. And now all you want to do is draw a line over here and a line over here, and just put the angles of what we just found. So 78.69 and 78.69. So the key idea here is to obtain as many solutions for the equation 2x plus 32. So we're going to have a bunch of them. And once we do that, we're going to write down all the solutions for simply x. Okay, so that's the objective here. So let's have a go here. So we've got a range between minus 90 to 90. Because we're working with 2x plus something, just imagine this range doubled to minus 180 to plus 180. Sorry for the bad handwriting, guys. Now, let's check this out. So let's go from here. So we always start from this x-axis here. So start from here. So we can go upwards once, which is 78.69, which is what we already have. So that's right here anyway. Another solution is that we can go backwards. So this would be 180 minus this value. So let me write here. 180 minus 78.69. And of course, because it's going backwards, it's going to be negative. The result will be negative. Another result we can do, if we start upwards, we can go all the way around and hit downwards. So that's a full 180 plus 78.69. So we also have 180 plus 78.69. Okay, so that's so far. We've got 2 results. Another thing we can also do is probably start from here, again from the beginning. So let me change color pen. Is go backwards all the way around until you hit this line here. So it's almost a full 360, but 78.69 short. So we can say 360 minus 78.69, but of course it's negative, so it has to be a negative outside. And that's it. I mean, we could try going more times around, but I believe if you tried going more times and then just solved it by, for x, you might not get you might have solutions outside the range. So anyway, to solve the rest of these, we look back at the original equation here, and all you simply do is literally for every single solution subtract 32 and then divide by 2. So when you do that for every single one, you should have the following. And I'm going to go ahead and just pause this and literally calculate myself. So yeah, so I've just found all the results. Now, just looking carefully at the interval again, so between x has to be between minus 90 and 90, just cross out the ones that's outside, like 113 and 156. And that's it. These should be the 2 solutions. So let's look at A. So using the identity for tan A plus minus B, show that tan 3 theta minus 45 degrees can be proven to look like that hand side. Okay, so we just first need to know what the expression for tan A plus minus B looks like. So I've did it over here. And well, this is actually tan A minus B. For the plus version, it's just the inverse sign. So it'll be plus here and minus here if we chose tan A plus B. Now, to make this look really easy, just look at both these equations. You can see that they look almost identical. The only difference here is that tan B seems to be 1. In other words, the B value representing 45 degrees seems to have a result of 1. So here we can just replace tan 45, and in the calculator this gives us 1. Remember, make sure it's in degree mode. That means this tan 45 is also 1. And replacing a with 3 theta, well, you're going to get the exact same expression. So it'll just be 1 plus tan 3 theta times 1. And that's it. That's literally proven. Okay, now let's look at the next bit. Okay, part B. Now, first things first, every time you see the word hence, always bring in the previous result. So that's why I copied it here, and always think about it for a moment. Now, looking at the question, it wants us to solve for a given angle, or at least a given range, the following equation. Now, when you look at this first time, you might think, okay, doesn't quite look familiar to the previous, but actually it does. If you rearrange this carefully by dividing 1 plus tan 3 theta across to make it look like this on the right hand side, you can see that this equation here is identical to the right hand side over here. Okay, now what that tells us is that you can immediately, and thanks to the word hence, replace this entire equation with the tan 3 theta minus 45. So that's why I got it over here. So all of this can be replaced by this equation over here. Now here, this is where the confusion might begin, or it might not. You notice that they both got tan, so probably, you know, instinctively you'd probably just cancel both the tans, which is actually okay. You do get a mark for that, but it won't give you the rest of solutions. What you have to think about is that what if you actually tan inverse to both sides? That is, suppose we tan inverse the right side. We did theta plus 28 equals, well, tan inverse of the tan 3 theta minus 45. And actually it goes both ways. I should have done it here as well. You're tan inversing both sides. Now, you know, as weird as this look, what actually happens here is that both sides cancel out, so all the tans disappear. So you're actually left with the theta plus 28 and the 3 theta minus 45. Now, thanks to the properties of tan, and this is actually some of the results. You could actually firstly just solve theta here straight away, and doing that would give us let's see, just, you know, subtracting 2 theta across, minusing 28, and then dividing by minus 2, you'll get theta equals 36.5 degrees, and that of course fits through the range. Now you have to be very careful because you could miss a whole solution. So remember, imagine this was just a regular question. If you tan inverse a problem, then you would most likely get a plus or minus 180. So think of this, plus or minus 180 degrees. This is what happens when you tan inverse. But then you might also get negative solution because you tan inverse both sides. So that's why I wrote plus minus 180. So then when you solve this one for plus, when you stick into this equation and solve it with the plus 180 or minus 180, you'll end up with minus 53.5 degrees, which is out of the range, or 126.5 degrees, which is. So the curve C has equation y equals ln of x squared plus 1 all over x squared plus 1, where x takes all real numbers. Okay, now for part A, we need to find dy over dx, and to find dy dx, you must remember that when you got a function over another function, we need to use the quotient rule. Okay, and the quotient rule is so easy. You literally just pick the top half as a u, the bottom half as a v. So just like I did over here, differentiate each one and then use a nice use a quotient rule method to stick them together. So let's have a go and simplify this. Yeah, now to differentiate the u function ln x squared plus 1, you simply just differentiate the inside, which will be 2x, and divide it by itself, x squared plus 1. That's how you differentiate every single log function. Okay, now for the second one, that's straightforward. It just becomes 2x. Just drop the power and you're done. Now the quotient rule tells us that we pick the v, smash it against the u prime by multiplying, then take the u, multiply against v prime, and then divide all of this by v squared. Okay, so let's have a look. So let's do v times u prime. So you got x squared plus 1 times this side, and you notice if you multiply this, you can actually cancel down x squared plus 1s. So you're left with just a 2x. And now we're going to subtract, because that's the rule, minus, and then we're going to subtract the other two multipliers. So it'll be 2x times the natural log. So I'm just going to copy it head on. And it'll be all over v squared. So it'll be x squared plus 1 all squared. And, well, there's not much to say here. You can see on the top line that you can just factorize 2x out. And doing so, well, you get this. And yeah, I've already done it, so that's it. Yeah, so let's look at part B now. Hence, and when you use the word hence, they always refer to make sure that you use the previous solution. Find the exact coordinates of the stationary points. Keyword, yeah? When you hear stationary word, think of dy over dx equals 0 and solve for x. And of course, when you solve for x, you can find y. Now, that's self-explanatory. So make it equal to 0. So let's solve this one equals 0. And when you do that, just remember that when this is set to 0, you can immediately cancel out every bottom fraction, because multiplying it across and times against 0, well, gives you 0. So the only thing you have left is the top line set to 0. And what does that tell us? Well, the first solution would be 2x equals 0, because this times that equals 0. And the second solution would be this function here, so I should put 2x here, equals 0 too. This means that the first solution, x is 0, so we can immediately find y, and I'll do that in a bit. And for this function here, you can rearrange to make the natural log the subject and solve. So let's have a look. First, to get rid of the natural log, you need to take exponentials on both sides. So taking e's on both sides, this cancels the ln and this raises it to the power 1. And you'll realize here that e to the power 1 is just e. And then to find x, well, you know what, minus 1 across and square root. And when you square root, always keep the plus minus result, guys, because this is the kind of bit where you can literally drop a mark. And this is what, 6 marks. So if you forget the minus sign, you could actually lose 1 or 2 marks. Now that we found x, all you need to do is literally plug into y, because remember, you're trying to find the stationary points, and that means you need to find the x and y solution. So let's have a look. So I already copied it down here just for convenience. So using the first solution, when x equals 0, plug in x equals 0 into this equation, you're going to have ln 0 plus 1 over 0 plus 1, and you're just left with ln 1. And that, if you're not too sure, in your calculator gives you a 0. So that means the y coordinate is 0 when x is 0. So that's our first stationary point. Now for the second, oh yeah, one thing I have to note, because I said plus minus, this means you have 2 more solutions. So essentially you have 3 solutions, including the 0. So let's have a look with the plus minus bit. Now, if you look at the equation, the y equation, you got x squares in there. So that means if you square this, you don't have to worry about plus minus, because you're going to get the same result. So that means x squared equals e minus 1. And plugging in e minus 1 in place of x squared, you're going to have this. And just tidying it up by, minus 1 plus 1 cancels out. You're left with ln e over e. And finally, ln e, again, if you're not sure, will give us a 1. Because ln and e cancel each other out. That means our y coordinate is 1 over e for both the plus and the minus result. So guys, make sure you put that down, and of course it's 0, 0. And that's it. We're all done. So by writing sec theta equals 1 over cos theta, show that the derivative of sec theta equals sec tan. Now, my tip for these kind of questions, yeah, every time you got a sec, a cosec, or a cot, always, and I mean it, always rewrite them in terms of sine, cos, and tan. Okay, it's because differentiating those lot are very easy, even though you're probably told how to differentiate them. Now, looking at this question, we want to differentiate sec, and it told us it's equal to 1 over cos. Okay, now I would use this because this can be easily solved using the quotient rule. And remember, the quotient rule tells us that we need 2 variables, a u, which is the top, and a v, which is the bottom. So we can say let u equal 1 and v equal cos theta. And now differentiating both of them, you're going to get, in 1 you get 0 because it's a constant. And differentiating cos is easy. It's going to be negative sine. And the reason of these two is that differentiating cos and sine always cycles back to each other. And that's it. Now, to use a quotient rule, you simply look at both the products and you just draw lines like this. So v times u prime minus u times v prime, and all over v squared. Okay, so therefore the solution is going to be, so d over d theta, and just put this out, is going to equal to what I just said. So v times u prime, so cos theta times 0 is 0, minus, so remember, you minus them, u times v prime, so 1 times minus sine theta, so it'll be minus, and because you already have a minus, there'll be plus sine theta. And all of this is over v squared, so cos theta squared, or cos squared theta. And of course, ignoring the 0, you got sine over cos squared theta. Now to make it look like the right hand side, just try and partition this. Think about how to get tan, because we know tan is equal to sine over cos. So just separating this as sine theta over cos theta times 1 over cos theta. We can see that this quantity here gives us a tan, and the right side, guys, gives us a nice little sec theta. Boom. And that's it. Okay, guys, now let's move on to part B. Okay, so given that x equals e to the sec y, so x is subject, show that dy over dx, notice it's not dx over dy, equals the right hand side, where this gx here is a function of ln x. Okay, so this one looks like we should go ahead and just differentiate, right? Now be careful, when you differentiate this, be careful not to write dy over dx, because x is the main variable. So this should be dx, oops, where's my pen? Dx over dy. Okay, now when you do this, this means that you're going to start making y the main variable. So let's go ahead and try and differentiate e to the sec y. Now if you guys are not sure, every time you differentiate a power, differentiate something that's an exponential, you always drop the power on the ground. So differentiating sec is going to be sec and tan, so it'll be on the ground sec y tan y, and then you just copy the exponential as always. Now all we want to do is just flip these guys over to get dy over dx, yeah? So this means dy over dx must equal 1 over everything I just said. Okay, now here comes the weird bits. So one thing we have to note is that everything inside a function has been converted in terms of x, yeah? And we got y's here. So looking back in the beginning, we noticed that x equals e to the power sec y, right? So we can already say that these guys here, this e bit, must be x, okay? That's cool. So what about sec y and tan y? Well, if we go ahead and just, rearrange this for a second, I mean, let's just go ahead and drop sec y to the ground. To do this, we can take ln on both sides. So let's take ln's. So if you do that, you're going to have ln x here. If you take ln on the right, you're going to have just sec y, because ln and e cancel out. So that's done. So now we can say that sec y here is ln x. But what about tan y? Oh, I wrote tay. So as for tan y, this is something we just have to try and spot here. You could use another relationship. So remember how we had the trig identity? We had sine squared, let's say sine squared y plus cos squared y must equal 1. You can make one in terms of sec and tan. To do that, all you do is just differentiate by cos squared. And if you divide everything by cos squared, this is going to become a 1. Oops, sorry, that's going to become a tan squared. Because sine squared over cos squared is tan. Cos squared over cos squared is 1. And 1 over cos squared will give us sec squared. Okay? And since we know what sec squared is, it's going to be ln x all squared. So let's go ahead and sort out here. So this means tan squared y plus 1 equals ln x squared. And now making tan y the subject, minus 1 is square root. You got tan y equals the square root of ln x squared minus 1. And I think that's it, because it says gx has to be a function of that. So let's go ahead and just replace the tan y with that. So you're going to have the square root of ln x squared minus 1. Okay, so let's stick this together for now. So this means dy dx is going to equal 1 over ln x root ln x all squared minus 1 x. Okay, now going back to the original function, notice how only x should be outside the square root. So because of that, we should kind of rewrite this ln x here. And to do that, you can of course just square it and then square root, because that's literally gives the same result. So this means we're going to have 1 over the massive square root sign of ln x squared from the first one times the second law, ln x squared minus 1. And of course, you can stick x over here, outside, just outside square root. So it'll be 1 over the square root of all of that times x. So here we need to express sine theta minus 2 cos theta in the usual r sine theta minus alpha form. Okay, so I'm not going to read the rest of this because this is the standard form. Now all you really need to realize is that when you start with a sentence, express and then in the form, it means that these two are equal. So let's go ahead and write that. So we know straight off the bat it's going to be sine theta minus 2 cos theta must equal r sine theta minus alpha. Now what you could do here is realize that this is one of those expanded trig forms, okay, in the form of sine a plus minus b, guys. Yeah, so always try and keep this in mind. So knowing that at least straight off the bat, then what we could do is say, all right, so this must be equal to sine theta, so sine a cos b, so sine theta cos alpha minus, and then opposite, cos theta sine alpha. So sine a cos b, cos a sine b, basically. And now we just match coefficients. So you'll notice that you're going to have a sine theta term on the left equal to a sine theta on the right, and then a cos theta here and a cos theta there. So the trick is to always match coefficients. So it'll be like, okay, hang on, for sine theta, we can say that we have a coefficient of 1 here on the left. On the right, we have a coefficient of r cos alpha. So we can say that for sine theta, 1 must equal r cos alpha. And then repeat the same for cos theta. We'll notice that we have a coefficient of 2 there. And by the way, they're both negative, so we can ignore negative signs. This has a coefficient of 2, and this has a coefficient of r times sine alpha. So 2 equals r sine alpha. And now, what you could do here is firstly, to work out r and alpha, let's go ahead and make everything to the usual SOHCAHTOA form, which is making sine alpha the subject and cos alpha the subject. So we're going to have, for example, cos alpha equals 1 over r, or sine alpha equals 2 over r. Now, thankfully with SOHCAHTOA, we always work with right angle triangles and just label each side appropriately. So for instance, for sine and cos, we can use SOHCAH. And of course, so I'll stick TOA for fun. Sine tells us it's going to be sine, the equation is going to be sine alpha equals opposite over j over hypotenuse. So opposite is 2, hypotenuse is r. So opposite angle, and here's the hypotenuse. And of course for cos it would be adjacent over hypotenuse, so it would be 1 over r. Okay, now to work out r, you just use Pythagoras. So we would say 1 squared plus 2 squared must equal r squared. And then if you square root that, you'll get r equals root 5. It looks like we're done. Now just replace one of these with root 5. So let's say sine. So you're going to have 2 over, well, or 1 over root 5. And then if you decide to sine or cos inverse either one, you'll get the same answer of roughly 1.107 to 3 decimal places. Okay, part B now. So just to let you guys know, I copied the entire equation from part A over here. So this is going to prove to be very important to this question. And now for part B, it wants us to find the maximum value of this equation here, and then the smallest value theta for which this maximum in the first part occurs. Okay, let's have a think. Now, one thing I want you guys to notice is that inside the bracket here, you can see it's 3 times bigger than this expression here. This means this is 3 times bigger than root 5 sine theta minus 1.107. So that's 3 times bigger. So we can replace that in a minute, yeah? So this means now, in order to find a maximum value, you can really just do it just by looking at the equation. You don't even need to differentiate, because that's what they usually want you to do. So if we look at the right hand side, we can see that the maximum value of this expression here, where the maximum value is sine, is always going to be 1. Why? Because in a sine wave, and again, this one will look a bit like this because it's shifted across. We can see that the highest point is a 1, but the lowest, the minimum value, will be negative 1. So we can essentially say that all of this here is plus 1 if we want to maximize it, yeah? So let's substitute everything back in the equation. So this means that the maximum value of m theta equals 40 plus, remember the constants are always the same. So instead of 3 sine blah blah, it's going to be 3 times the right hand side. So it'll be bracket 3 root 5. And instead of writing sine, the maximum value sine is 1, all squared. And that's it. And then you just smash in the calculator and you should get 85. Done. That's part A done. Now for the second part, to find the smallest value, just go ahead and differentiate the equation. So again, rewrite the equation neatly. So we're going to have m theta equals 40 plus, and instead of the expression here, it's going to be 3 root 5 sine and then blah blah blah, yeah, all squared. Just leave us 3 dots. That represents everything inside there, yeah, that theta minus 1.107. Now to differentiate that, actually we don't even need to differentiate, because you got the maximum values 85, we can equate this equation to 85. So we can say 85 equals 40 plus 3 root 5 sine blah 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 all squared. And then just solving to make sine the subject. So subtracting 40, you get 45. Square root, so you get plus minus square root 45. Equal, and divide 3 root 5 equals sine blah blah blah. Sine inverse this. Remember, you got plus minus. You're gonna get inside the blah blah blah. So theta minus 1.107. You're gonna get what is it? Pi over 2 or minus pi over 2, and that's it. And then to find, and then it tells you that the angle has to be between 0 and 2 pi. So if you have to make theta the subject, you're going to add 1.107 across. So of course you're not going to use this one here. That's not going to work, because what is pi over 2 actually in radians? It's always good to check what that is. I could be wrong. So pi divided by 2 is 1.1507. Yep, it wouldn't work. So adding this across, theta is going to equal pi over 2 plus 1.107. Okay, that's about 2.6. How many decimal places? Wow, whatever, 78. So that's the kind of answer we're looking for, 2.678. So C, find the maximum value of the similar looking questions like A and B. Okay, now I've copied the pi expression over here. All you can probably notice here is that the sine 2 theta minus 2 cos 2 theta is kind of identical, except now that the angle theta is double. It's 2 theta, 2 theta. So this means that inside the sine, this theta will also be 2 theta. So you can literally rewrite all of this bit here as root 2 theta minus and then 1.107. Yeah, that's really it. And of course that's all squared. Now to maximize this, just like the previous one, we just have to ask ourselves that what value of sine can we take? Well, since we know this is just a regular sine with whatever inside, it's going to go between -1 and 1. But be careful here, because it's really dependent on what you go inside here. And don't forget, we're going to square this value. So if you choose a positive or negative and you square it, you're still going to get positive. Now the tip for fraction questions, when you got a value underneath on the denominator in the lower part, you want to try and minimize the value as much as possible, because the smaller this value is, the greater the final result. Because a big number over a small number will give a bigger number. Okay, so the only way to get this to the absolute smallest is to take it to 0. So this means that to maximize n, we need to make sure this sign part is 0, because 30 over 5 plus 0 will give us 6. But if you chose 1, for example, you're going to get something like 30 over 5 plus 2 times root 5 times 1 squared, and that's going to give you an answer like 2. So basically just make all of this 0, and doing that you're going to get n. The maximum value of n is going to be 30 over 5 plus 2 root 5 times 0 squared, and this is going to give us 6. So I couldn't think of a bigger solution. If you chose a negative number, again, it wouldn't work. So yeah, just keep testing values until it makes sense. I would test 1, -1, 0 and see what gives you the biggest output. Okay, and the final part of the day. So second part, find the largest value of theta in the given range at which the maximum value of n occurs. So again, this means using the result from part I, plug in 6 there and solve for theta. Literally it. Okay, let's do this. Whew, I can't wait to finish this. So it'll be 6 equals all of that, equals 30 over everything at the bottom. So all you have to do, guys, is just simply rearrange. So let's multiply the denominator across. So 5 plus 2, etc. across to the left side. So you're going to get 6 times all that. So 30 plus 12. Instead of sign, I'm going to put the root 5 sign bit, yeah? So I'll just do dots. Squared must equal the right hand side, which is 30. Okay. So more or less, just solve this. So subtract 30 across is 0. Divide 12 is still 0. Square root is still 0. So you're left with the dots, which is the sine term, which is sine 2 theta minus 1.107 equal to 0. Okay, so that's when you subtract 30 and so on. And then sine inverse that. Sine inverse 0, I know for sure is 0 degrees. So 2 theta minus 1.107 equals 0, well, radians. And then to find the maximum, it's probably best to use the sine diagram, the cast diagram. So this means we're going to go through here and S, because S is sine. Well, because the angle is 0, it's literally going to be, well, this angle is going to be 0, so it's literally going nowhere. So it's going to be 180 minus nothing, or pi minus nothing. So it'll be 0 pi. So your solutions are either pi or 0. So actually, it's probably a good idea to probably still cycle around. And the reason why I say this is because we've got 2 theta here. So this means that instead of working with theta, we're working with 2 theta. And this is, of course, twice the angle width. So it would be between 0, 2 theta, and 4 pi. I mean, this is just telling you how big theta is. So essentially, you could go around more times. So since we know the angle's flat, I mean, you just go around here to pi. You're going all the way around to 2 pi. You could even go around an extra time. So that's pi plus pi plus pi, so 3 pi. And again, 4 pi. So your solutions are pretty much in terms of pi. So pi, 2 pi, 3 pi, 4 pi, and so on. Now we just need to be careful because we can only use some of these values. And now that's it. So you got a bunch of solutions. Literally just add 1.107 to each of them and divide by 2. And then you'll realize that you can go all the way up to 3 pi. So this would be the optimal solution. So you would say, okay, therefore solving this, theta equals 3 pi plus, oh god, slowing down, 1.107 all over 2. That's it. And this would give us about 5.266. And this is literally just less than 2 pi, less than or equal to 2 pi. Because 2 pi is actually roughly equal to 6.283. Yeah. And if you actually use 4 pi, by the way, if this was a 4 pi here, for example, then, oh, but my mouse is falling off. If this was 4 pi, then the actual solution will end up being, I calculated already, 6.8 something, which is obviously not less than 2 pi. So again, the final solution will be using 3 pi value to get 5.266. And it's finally over. Yes. Whew. Well, guys, I mean, I just want to say that this paper was definitely easily top 3 hardest C3 papers I've actually ever written, ever solved. There was a bunch of maximizing problems, and well, the other questions I don't even remember anymore, but they weren't easy, that's for sure. But anyways, I mean, I'd like to know your thoughts on the paper as well. I mean, I'd like you guys to tell me how you found it, and any particular questions which were challenging. Because overall, this was a mixed bag. It was definitely a mixed bag, and it's definitely ranked as a top paper. But you know what? I mean, it's done. So yeah, other than that, guys, I mean, I'm gonna definitely rest now. I got C4, and if you guys are still watching the rest of my videos, definitely check out the C4 video. Okay. If it's not launched by the time I record this, it will be launched soon. Otherwise, if it is launched, after some time has passed after the upload of this video, then check that out. I'll be there, and you can chat to me anytime. Otherwise, have a lovely day. Good luck with your revision, and get into uni. You can do it. Just keep focusing hard, and you'll make it. Otherwise, take care, guys, and have a lovely day.